Okay. Hi, everyone. So did anyone calculate the stress for the end of the problem yesterday? Whatever you get. Anyone? 55 MPa? Like 75. Anyone else get that? 76. 76, yeah. 75.99 as well. For the 190, that is. And so just double check you put a rotary out in front of everything. Just make sure. If you have any issues, come see me. There's every chance. Well, if a couple of us got that number, I'll be more confident than just me. So see how you go. Yeah. All right. So today, what we're going to do is the bending equivalent. So yesterday we talked about torsion. And we had that example. Today we're going to talk about bending, and I've got an example, and then I've got a relatively simple example that has both bending and torsion. That if we get time, we'll work through. Otherwise, we can sort of do part of it. But when we talked about torsion, we talked about sort of the plane of the weld group and where that centroid was. And any load that's in plane but away from the centroid is going to cause that torsion. Alright? Now bending is anything that's in line with the centroid but is out of plane. Okay? So you can see this load here out on this little cantilevered bar. It's in the centre of that bar, which means it's in line with the centroid. But because it's out from the actual plane, it's going to want to tear that weld off the wall. Alright? Now, when we talk about combined loading, if I was to move that load over to the side there, then you'd have the cantilever, so you'd have your component of bending, but then you'd also have, if it's off from that centroid, you'd also have the torsional component as well. Alright? So we can have anything, any movement in plane or away from the centroid this way. Is torsion. Any movement away that way that's in line with the centroid is bending, and then when you have some combination, you'll have both bending and torsion. Okay? Well, we'll deal with just the bending for the minute. Alright, so we deal with it in almost identical way to what we do with torsion, except we use our bending equation rather than our torsion equation, funnily enough. And in this particular case, we replace whatever force is causing the bending load with an equivalent shear like we did before, and this time we have an equivalent moment rather than an equivalent torque. So our force that was out here on the cantilever gets replaced with a downward V in the same direction and a bending moment M that's going to roll the weld in the same direction as that force. And the result is, once again, primary shear. So with torsion we have primary shear as well. So we've got that primary shear everywhere throughout the weld, and the magnitude of that is just calculated with V divided by the area. And now we have normal stress rather than shear stress resulting from the bending. And normal stress, if you look at the bending moment down there, it's going to want to put that top weld in tension and the bottom weld in compression. If it was going up the other way, obviously it's reversed. And those are tensile stress, sigma. And sigma is calculated using MC on I, like we always use. M is the equivalent moment, C is the distance from the centroid to whatever you're looking at. So in this case, it's a perpendicular distance from the centre plane, exactly the same as for shafts and beams and everything. So effectively the bending stress will be exactly the same for that top section and for the entire length of the bottom section because they're parallel to that neutral plane. And then once again, I, our moment of inertia of the weld group, we can calculate if we knew the area, and if we don't know the area, once again, we use the unit moment of inertia of the weld group. And if you all pull out your weld tables, which I'm sure you've all brought to your lecture, table 7.2 is your bending version of moments of inertia. Now, you guys will all remember from the classes where you've learnt about moment of inertia and things like that, that torsional, so polar moment of inertia, doesn't matter what orientation the shape is because it's round in a circle, so you have the same value regardless of your orientation. But bending moment of inertia is different if you are bending sort of up and down as opposed to side, yeah? So bending on a channel this way, down, is very different to bending on a channel this way, down, in terms of the moment of inertia. You have different moment of inertia in each direction. Everyone's remembering that? So the reason I highlight that is because if you look on your table 7.2, we've got a straight line, obviously, so that's a simple case. The next two are our parallel welds. One's straight up and one's horizontal. Alright, exactly the same weld group, but it's just the orientation. And in this particular circumstance, each one of these is the bending is sort of in the perpendicular, the vertical plane. Okay, so if you have bending on the parallel welds up and down and it's in the same direction as that, you use this IU. If you have bending and your welds are in the horizontal plane, you use this IU and so forth. The next one you'll see you've got the channel, so C shape in the horizontal, C shape down like that, and it will be exactly the same as if it's up like that, so you just need to get the right plane. Then we have a rectangular shape, we have what would be an I-beam weld, but if you left the bottom off it, and then an actual authentic I-beam weld, and then a circle. So those are the major ones that we'll have to deal with, and we'll have a go at that in a minute. Alright, so you guys had a go at, or we worked on the board on the torsional variant. The bending variant is basically identical in workflow, and the only difference is when we calculate von Mises. You remember, so this is the one we did yesterday, this is torsion. So von Mises is the square root of 3 times the, that x component, the y component of those torsions squared. Well, if now you have a primary shear and a tensile bending stress, then this is the same type of von Mises equation that you're quite familiar with. The tensile stress squared plus 3 times the shear stress squared, or square rooted. And I've put also on this diagram the case where you've got all three components of stress. So it's just a combination. So we've got the tensile, if you have the tensile stress, and you have, let's say, a horizontal component from, combination of your shear and, well, your primary shear and your secondary shear, and some vertical component, combination of primary and secondary shear. Then you calculate the von Mises bending or tensile stress squared plus 3 times the, this component here. So it's just a combination of the two. Quite simple von Mises calculations. Cool. So, might be almost all I have in terms of these ones. Yeah, so let's do an example on the bending, and then we'll have a go at sort of the combined case and go from there. so we have some rectangular weld group. We've got E60 welding rods, which in this case we're going to use SY equals 345 for the specific welding rod that we're using. We're finding the weld size for a factor of safety of 3. Tend to use factor of safety of 3 quite a bit with welds just because of the unknown factors around, how good was the actual weld process, was there bubbles and crap left in it, or was it a really good welding process. But that's, it's really just case specific. Let's do a bit of a schematic. Alright, so the force is applied, that's a hole, so that would be a pin, and maybe you have a clever see the side of it or whatever, but the equivalent or the effective force will be applied at the centre of that pin. Might be distributed across, but as far as the bending is concerned, it's all the same. And the last thing we need to do is indicate how far out that is. That cantilever is 160 millimetres. And then we should draw some room. Say H, so that's weld on sides. H, so that's top, bottom, left and right with 2 arrows. And I've got everything. Yep, good enough. Alright, what's the first thing we do? What's the first thing we did yesterday? Yep, one centroid. We know what a centroid is? Yeah, I don't pretty good guess at it. So we know where the centroid is because it's a simple shape. We'll quickly pull out our bending tables and make sure, but for this shape, it's pretty obvious. And once we've got the centroid, we will find equivalent loads at the centroid that we can then use to calculate our stresses.
For these welding problems, are there any assumptions you should?
Yeah, you probably should. What's a good assumption? One, welding processes of a very good quality and elastic and homogeneous as a result of full penetration welds. Again, you've probably got weight is negligible on the actual component itself, otherwise you'd have to take more loading into consideration. Anyone else think a good one? What else have we got? Yeah, probably heat affected zone is negligible. Certainly with fatigue, we'll say that, because if it then becomes non-negligible, that's a problem. No residual stress resulting from welds. Yeah, so there's quite a few little assumptions there. In any one of these type of questions that I'm marking, even quiz questions, if you're not doing the initial layout all the way in a quiz or exam, you still need to put those assumptions. I'm being lazy here because I'm showing you how to do it. But about 3 assumptions is the bare minimum for you to get full marks for the assumptions, right? So material being homogeneous and elastic, weight being negligible, and one other is generally, if it's a shaft, then you talk about transverse shear potentially or whatever. If you've made any other assumptions, please write them down. But we do that at every point. I really should do that. Let's do that. Alright, so what do we say? Material is elastic and homogeneous. Welds are all of high quality. Full penetration. What else did I say? No stress, no residual stress resulting. Weight is negligible. It's probably a good set to start with. All right, solution. So we're first of all, we're going to replace the loads with equivalents. Alright, and so I'm going to draw my weld group down here. And centroid, this distance are known to be half of those on the layout, 35 and 60. Then I've got an equivalent shear down at the centroid and equivalent bending moment that's sort of coming down the page. B in an M. B just equals 15,000 newtons, which is easy. And M equals 15,000 newtons times our lever arm, which is 160 mils, 0.16. That equals 2400 newton meters. Alright, everything we know about bending and transverse shear technically, where do you reckon the maximum bending stress is going to occur? Top, bottom, and because we know about bending, we know that it will be maximum all the way along the top and equal, and maximum all the way along the bottom, compressive and equal. Arbitrarily, I normally choose tension over compression, just because arrows out are easier to draw than arrows in, so choose whatever you want. But let's just analyse one point on the top edge of that weld as our candidate critical element. And I will say that and put some sort of justification in, so max bending stress will occur at top and bottom. Choose top to analyse. like to sort of redraw it and then draw my stress vectors on it. I can redraw the whole thing, or I can just draw a top edge. Remember yesterday we drew those stress vectors on the whole shape of the weld, and that was largely because we had a couple of potential candidates. Did anyone analyse that other point? Was that more or less critical? Did anyone do it? At some stage between now and next lecture, I advise go and do that other point. It would be a good study for the torsional thing, and I'd like to know whether it's more critical or not. I'm pretty sure it's not, because I ask that every year and no one comes to me and tells me I was wrong. Alright, so that's a primary shear and that's a bending stress. Primary shear equals B on A, which equals 15,000 on T times T times the area. What's the area of our total weld? It's just the total length, yeah. So 2 times 70 plus 2 times 120. 0.07 plus 2 times 0.12. And I get 39473.68 on T, and I always write my pascals next to it so that when I get to the end I don't accidentally equate that to a megapascal. Alright, bending stress. Sigma equals MC on I. And our values, M equals 2400 Newton meters, C equals half the height, which is 0.06 meters, I equals T times IU, and we need to calculate IU from our sheet. D squared on 6, 3B plus D. Alright. Everyone calculate that, tell me. Check to see if I got the equation right. Trust no one, ever. Especially me. It's good practice though. If you have a senior engineer who's, you know, RPEQ and CPEng come to you saying, here's an equation, check it. He's got 15 years experience and that's completely fine. Good engineer checks it. Don't check it in front of him and make it obvious if you think he's wrong. But if you're going to have to rely your work on something you've been given, trust no one, ever. Or use it, get a calculation, and then find a different way to calculate the same thing, which is always good practice and make sure that it's right. Alright, anyone got a IU yet? 792E -6 meters cubed. Very good. Alright, so that going in, sigma equals 2400 times 0.06 on T times 792E -6. And I get 18.18 on T in pascals. Are we good with that? Yep. Alright, what's the next step? Have I got all my stress values? a failure criterion yet? On my six, yeah, I'm going to do on my six first, and then I can compare to my static failure, and I'm done. Alright, so on my six stress, sigma dash equals square root of sigma squared plus 3 tau squared, put that out, equals, so we got a 1 on t squared and square rooted, a 1 on t squared and square rooted, so that just comes straight out the front. And sigma is 18 squared plus 3 times our tau, which was 39, whatever it is. Squared. And I get 1 on t 194,248.20 pascals. Which is not that much more than just a bending stress. Alright, we good? Yeah. Alright, so next thing, simple equation, static failure. Yeah, static failure, which is just on my is equals sy on n. So 248.20 on t equals yield stress, which is 345 E6, and factor of safety was 3. Therefore, t equals 1.69 e to the minus 3 meters equals 1.69 millimeters. Am I done? What's the question asked for? Size of the weld, which is h length. Okay. Should h be bigger or smaller than t? H. Bigger. There you go. H should always be bigger because that's the bottom of the triangle, whereas T is the smallest area. T is always associated with the smallest area because the smallest area gives us higher stress. So, H equals T on 0.707 equals 2.39 millimeters. Does everyone remember what I said yesterday about what we do with millimeters in terms of welds? Firstly, we round them up to the nearest millimetre, so that gets us 3 millimetres. And then, if it's less than 3 millimetres, we round up to 3 millimetres. But we're there already. So at the end, we'd say, therefore, specify 3 millimetre welds. There you go, so let's go back to our engineering judgment for a second. Think about what a 3 millimetre weld looks like. That's pretty small. Nice little tight weld. And what's the dimensions of our thing? So we're talking 120 mils. I don't know, I don't rule, but that-ish. By 70 mils, that-ish. And 10 to 11, 160 mils, that-ish. And we've got 15 kilonewtons, which is the same as 1.5 tonne hanging off the end of it. Okay. So about that 1.5 tonne, you've got 3 mil welds around there. Okay. So you start to see sort of how strong those welds can be in static failure. And remember, that's only to get to yield too. That's not ultimate. So ultimate might be another, I don't know, 15-20% on top of that load carrying capability. So welds are very strong. I mean, steel is very strong. If you had the steel as a single piece, you'd be pretty confident that that amount of steel could carry, 1.5 tonne. But as soon as we start talking in welds, you inherently distrust welds, which is right because you should inherently distrust welds. But the analysis tells us that they're very, very strong. David. Alright. So who's feeling confident to do one of these without me doing it on the board in front of you? That's what we're going to do. And we're going to do a combined one, but it's going to be an easy combined one to start with, and then we'll do a more complex one in the tutorial on Monday.
And then more complex on that.
And then potentially a more complex one in the big set. But there are lots of examples in the textbook for you to practice. With this quiz will cover fatigue of shafts, and it will also cover welds. And next week we're going to do fatigue of welds, which is basically just exactly the same as what you did with shafts, except we calculate sigma A and an M rather than just a single value. So you're doing the same thing over and over and over again. But there won't be any weld fatigue on the quiz. It'll just be, if I do 2 questions, it'll be a relatively simple weld question and a more complex shaft question. Or I could do one complex question on one or the other. So study it, is what I'm saying, I guess. Generally one big and one small, or one medium and one small is what I ordinarily do.
So you're talking about
Is that next week? Yeah, it's next. So, yeah, I think the Tuesday lecture, that's when we'll do fatigue of welds. And an example, and fatigue of welds is literally one PowerPoint slide, which is, this is how you calculate SM slightly differently for welds, which is largely related to their different stress concentration. But otherwise, it's exactly what you've done. So we're just doing it to a different machine environment. All right. Yeah, so we'll do fatigue welds, then we'll do bolts for a couple of weeks. We'll do gears for a couple of weeks and we'll be done. As you'll see, by the time we go through bolts and gears, you'll see that we're doing literally the same workflow every single time. So what are the forces, how do you characterise force? What are the stresses, where's the critical stress, what affects that? How do you compare to the failure criterion? What are sigma A and sigma M in the critical zone? Is it failing? That workflow repeats for literally every machine component. Your textbook has about 10 different types of machine components. We're doing the major ones so that you'll be really familiar with those. But when you come across something else like a V-belt or something like that, you just apply exactly the same procedure. Maybe refer to your textbook for some of the finer points like stress concentrations and things, and then go on your merry way. It's exactly the same. So once you have this workload down for one thing, that's what you apply for everything. Right. Right, so the diameter of this bar, which also dictates the diameter of the weld group, is 50 mil. got a load of 1,000 newtons and some dimensions. 10 litres out that way and 10 litres out that way. So that's 200 millimetres out and 100 millimetres across. And we have a weld here. I'm not entirely sure how to specify a circular weld. I'm just
Put a circle on the end of the, you know where your arrow turns?
for that.
Put
There.
a circle around that and lean all around.
All around. Okay, cool. Do I leave that triangle there? Yeah, cool.
And same with the other one, that last question you had, instead of putting 2 in there, you put the
You
1.
do a circle and it says all the way around. There you go, perfect. Cool. I think that's all I need to give you. Alright, so we've got a circular weld group here, obviously. If this load was just on this end here, it would be obviously just bending, and you just have that cantilever do exactly what we did in the previous one. If the load had, if this was some plate out to the side here, and the load was just here, you just have total torsion. As it is, we have torsion and bending and the primary shear from the shear stress. The procedure will be exactly the same. So firstly, find the centroid of the weld group. Is everyone comfortable doing that? Pretty straightforward. Find an equivalent. In this case, you'll need an equivalent bending or equivalent moment, an equivalent torque and an equivalent shear, which is all fairly straightforward. This is stuff you've done a million times before already. And then you need to work out where the critical zone. So torsion, where's that maximum for a circle? Whole perimeter. Yeah. Shear, we're saying that for welds the shear is even everywhere. We don't have that profile where it's max in the middle and minimum on top and bottom because we don't have the whole profile. We don't have the whole sort of continuum for it to distribute properly. It's just a narrow weld. The only way it can distribute is to distribute evenly, which is mostly accurate. So that would be even everywhere as well. So torsion and or our primary and our secondary shear are even everywhere. Where's our bending maximum? Top and bottom. So already we can look at it and with our good engineering eyes work out which is our critical element to analyse. Work out the primary shear, the secondary shear, the bending stress, what mice is it, and then compare it to the fire criteria. Easy enough? Go. And I might even, I'll just put the, that's in the way, so I'll put the 1/6 equation up for you just here when you get to it. Just in case you didn't copy it down quick enough. Sigma squared plus 3 tau. Now I'll say, in this case, it would be Z. And then this one would be ZX, and this one would be ZY, or vice versa. Now remember that those are the coordinates that actually line up with the Cartesian coordinates, those two shear stresses. This isn't primary shear and secondary shear. Primary shear and secondary shear are vectors, and so they can be close together or far apart or whatever. This is, once you have primary and secondary shear, you boil them down to their x and y components, and then you add all the x's, add all the y's, and substitute results into those 2 points. Okay? So don't get mixed up and just accidentally throw primary and secondary shear into that equation, because it won't work, it'll screw everything up. Alright, so those are x and y components. And in this context, in the 3D context, the tensile stress is in the direction of z, and then the two shears are on the z face, one in the x direction, one in the y direction, which is why those subscripts are the way they are. Cool? Alright, have a crack at that. We'll see how far you get. Give it 10 15 minutes with me in the room to help you. And then you guys, if you haven't finished, can finish your homework.